The principle of total potential energy is one of the most important and vague topics in finite element analysis. In this presentation, we're gonna go through all elements of total potential energy. I hope that this tutorial will clear up questions you might have about this principle. Before we get into the details on all that, make sure you watch all the way to the end of the video for complete understanding of this principle. Here we will be covering the potential energy, the strain energy, the total potential energy, the principle of stationary or minimum potential energy, admissible variation, boundary conditions, and a complete solved example. Let's start off with potential energy omega and consider an elastic spring of stiffness K, with one end is stationary and the other end is free. Now let's assume that an external nodal force P was applied to the spring in the positive x direction of the system. Notice that the positive x direction is in the same direction of the gravitational acceleration. The external nodal force P will cause the spring to stretch or deform an amount of d in the same direction to the direction of positive x. The corresponding external work, WE, done by the external nodal force will be P times D. The potential energy omega of the external force is opposite in sign from the external work WE. In other words, WE equals the negative of omega, because the potential energy of the external force is lost when the work is done by the external force. Therefore, omega equals minus WE equals minus P times D. For example, when you do weightlifting or when you pull or push loads, you perform work, but in the same time, you lose potential energy. If the external nodal force P was applied to the spring in the negative x direction of the system, the spring will compress or contract an amount of d in the opposite direction to the direction of positive x, and the corresponding external work WE done by the external nodal force will be P times D. The potential energy omega of the external force is similar in sign to the external work WE. In other words, WE equals omega. This is very similar in essence to increasing the potential energy of a weight by raising it. Therefore, omega equals WE equals P times D. The potential energy omega is the capacity of forces such as body forces, surface traction forces, and applied nodal forces to do work through deformation of the structure. How do we know if omega is positive or negative? Rule of thumb: replace the external nodal force with a weight of equal magnitude. Remove the attachment between the applied weight and the spring. If both the spring and the weight move in the same direction, then omega is positive. If the spring and the weight move in opposite directions, then omega is negative. strain energy U. The strain energy is the energy stored in the deformed structural member and can be calculated by computing the area under the load displacement curve or the area under the stress strain curve. Although the external applied load is always acting at its full value P, the spring itself, however, will experience a gradual increase in load or stress and displacement or strain. The lower left figure shows the load displacement curve for linearly elastic material. Notice that the slope of the load displacement curve is K. The lower right figure shows the stress strain curve for linearly elastic material. Notice that the slope of the stress strain curve is E, where E is the modulus of elasticity of the material. For linearly elastic materials and gradual increasing load, the strain energy U is 1/2 times F times X. This equation is nothing but the area under load displacement curve, where F is K times X. Now if we substitute for F, we will get an equation very similar to what we have in equation 1. The most generic form of equation 1 is the triple integral of the area under stress strain curve with respect to volume, dV. For linearly elastic material, this equation can be rewritten as the strain energy U is the capacity of internal forces or stresses to do work through deformations or strains in the structure, or the energy stored in the deformed structural member. Now let's move on to the total potential energy pi p. The total potential energy pi p is defined as the sum of the internal strain energy U and the potential energy of the external forces omega. That is, pi p equals U plus omega. Principle of stationary or minimum potential energy. This principle states that among all admissible displacement configurations of a body, the one that satisfies the equations of equilibrium makes the total potential energy minimum with respect to small admissible variations of displacement. Based on the statement above, the equilibrium exists when delta pi p is 0 for arbitrary admissible variations in displacement delta di from the equilibrium state. Please note that delta pi p is the total change in the total potential energy. Hence, to satisfy delta pi p is 0, all coefficients associated with the delta di must be 0 independently. The last paragraph can be expressed mathematically as follows. If the total potential energy pi p is function of n number of displacements d1, d2, d3 up to dn, then the total change of this function pi p will be the partial derivative of pi p with respect to d1 times delta d1 plus the partial derivative of pi p with respect to d2 times delta d2 plus the partial derivative of pi p with respect to d3 times delta d3. The summation continues until the partial derivative of pi p with respect to dn times delta dn is reached. The last equation can be rewritten as delta pi p over delta di equals the partial derivative of pi p with respect to di, where I is a positive real integer number from 1 to n. To maintain stationary or minimum potential energy, these two terms should equal to 0. Differentiating pi p with respect to d1, d2, d3 up to dn, and equating each term to 0 to minimize pi p, we obtain n-element equations. Figure 1 is a graphical representation of energy relations when the total potential energy pi p is function of one displacement variable. Notice the horizontal axis is the displacement d, while the vertical axis is the energy. The parabola is the strain energy. The straight line is the potential energy, and the dashed line is the total potential energy. The stationary value is located at distance d equilibrium equals p over k. The stationary value is the minimum value of the total potential energy. Can you prove it? Earlier, we came across a phrase, admissible variation. What is admissible variation? An admissible variation is one in which the displacement configuration satisfies 1. The essential boundary conditions, and 2. The continuity condition or internal compatibility. The essential boundary conditions are simply the support geometric conditions. There are two types of boundary conditions. 1. Essential boundary conditions. 2. Non-essential boundary conditions. An admissible configuration needs not satisfy non-essential boundary conditions. In this example, we have a cantilever beam subjected to a concentrated force P. The essential boundary conditions in this case are: at x equals 0, the deflection and the slope of the deflected shape should be zeros. The non-essential boundary conditions are: at x equals L, the bending moment and the shear force should be zeros. The upper curve is inadmissible configuration because it violates the two essential boundary conditions. It also violates the continuity equation at two locations: the discontinuity at A and the gasp at B. The lower two curves are both admissible configurations. However, only the lowest curve seems physically reasonable. Please note, neither of the lower two curves need satisfy the non-essential boundary conditions. In this example, we have a prismatic bar of length L under tension. The essential boundary conditions are: at point 0, 0, the axial displacement u should be 0, and at point 0L, the axial displacement u should be greater than 0. Figure 3a shows the actual and admissible displacement configurations. Notice that both curves satisfy the essential boundary conditions and the continuity condition. Figure 3b shows inadmissible displacement configurations. The upper curve is inadmissible because of the slope discontinuity at this point. The lower curve is inadmissible because it does not satisfy the essential boundary conditions. Example. In this example, we have a linear elastic spring subjected to a force of 1,000 pounds. It's required to evaluate omega, u, and pi p for various displacement values. It's also required to show that the minimum total potential energy corresponds to the equilibrium position of the spring. Solution. Pi p equals u plus omega, where u is 1/2 times k times x squared, and omega is negative p times x. If we substitute these two equations into the pi p equation, we can get pi p equals 1/2 times k times x squared minus p times x. Now we can substitute for the unknowns, k and p. In this case, pi p can be rewritten as pi p equals 250 times x squared minus 1,000 times x. Differentiating pi p with respect to x and equating the result to 0, the minimum total potential energy can be calculated. Notice that in this example, pi p is function of one variable, which is x. Therefore, the partial derivative can be replaced with the total derivative. The result will be 500 times x minus 1,000 equals 0. Now we can solve for x. If we do so, we can show that x is equal to 2 inches. Now if we substitute x into the pi p equation, we can get the minimum total potential energy. In this case, pi p equals 1/2 times 250 times 2 squared minus 1,000 times 2. The result will be negative 1,000 pound-inch. This figure shows the potential energy, the strain energy, and the total potential energy. Please pay attention to the total potential energy, or the minimum total potential energy. It occurs when x equals 2. This deformed position also corresponds to the equilibrium position, because if you substitute x equals 2 into the equation of minimum pi p, you will get 0. In other words, the partial derivative of pi p with respect to x equals the total derivative of pi p with respect to x, and the result will be 500 times 2 minus 1,000. The result is 0. It means we reached the equilibrium position.